Thanks for joining us this morning, everyone, guys, for our sustainability. Our presenter this morning, as we'll carry out our same format as usual, is Marina Aburas. I got that correctly? Fingers crossed, maybe. Marina's graduated from the University of Adelaide with an honours degree. But before I get too far ahead of myself, Yaara, our acknowledgement of country, please.
Please, let's acknowledge that the land that we're meeting on today is Tanzania, land of the Ghana people, and we pay our respects to the elders, past, present, and emerging. And we admire greatly their connection to country and wish to learn from it. And we also wish today to learn from Marina about her fascinating topic of
smart facades.
Thank you.
Thank you, Yaara and Tyler. And thank you, ASBN, for having me here today to speak about smart facades. In particular, you'll see smart facades have multiple aspects. My research into investigating thermochromic glazing technologies from fabrication through to implementation. So before I delve into the details, I thought I'd give a really brief background about myself. So I'm currently working as an architectural business development manager for Blue Scope Building Components. But before that, I did my bachelor degree in civil and architectural engineering before branching out to work as an architectural engineer on some residential projects, coming back to the University of Adelaide and the University of Nottingham to do a joint degree in architectural science looking at these smart facades. Even though I was the PhD student and therefore the lead researcher on the project, it's definitely a team effort doing research studies. So a shout out to my primary supervisor, Professor Veronica Sabardo, I could see is in the audience here today, and my co-supervisors, Professor Terry Williamson, Professor Yupeng Wu, and Professor Heike Ebden, whom without the research couldn't have been conducted. So a little bit of an outline for the talk. I will go into a general background of my understanding of smart facades, delving into the material development because we actually developed some coding, so got our hands dirty in the lab, took the values from those coding developments into a building simulation, and then kind of opened our minds a little bit and went, hey, we've developed these codings and we've simulated how they act, but what do people think of these smart facades? So a little bit of architectural psychology here for you, before ending on a where to next, so that hopefully we can open the discussion. There's myself, but there are so many experts in this conversation so that you can, we can figure out where the world of smart facades is going next. So a bit of background. A little bit of fun one for the chat. Can anybody see a common denominator between the three of these buildings on your screen? Just tap it away, and once I see the right answer, I'll go to the next slide. The chat there. Whoa, glass, glass, glass. That's absolutely right. They are all glass buildings. They're all glass envelopes. One thing that you've just seen revealed at the bottom there is where these buildings are located. So they all look almost identical from a materials being high glass skyscrapers, but they're located all the way from Hong Kong to the Middle East to Sweden. And that's kind of a common thread that we see in today's skylines, that even though we've had technological evolutions and people should be aware of sustainability, environmental quality, you still have designs that pay little attention or have it as a second thought as to where the building's situated and how it's going to act. And here you see a little bit more technically the breakdown of the heat gain through various building envelope components for an office building. And you can see that the heat gain through windows contributes to about 50% of that. And that's an international problem where the US Department of Energy estimated that 30% of the energy that's used to heat and cool US buildings is lost through inefficient windows. So to put a cost figure on that, that's about $42 billion in the US annually for the US alone. So that's a lot of money. I understand you might say, hey, that's one aspect. Maybe cost isn't your incentive. So take a look at this. Here you see what happens when buildings are designed without occupants in mind. So you can see umbrellas spotted being used by students at a public library in Shenzhen in southern China, because the building has floor-to-ceiling glazing, exposed to sunlight, and they have to make do with what they have. So if you want to avoid that, the general idea is that you want to intercept that direct sun before it enters the building. And there are different ways to do this, but a notable and effective way to do that is through shading. So there are different types of shadings. You can have interior shading, exterior shading devices, up to the discretion of the architect. And you can see some standard types on the left there, different types of shading devices, and a more innovative one on the right, which is Al Bahar Towers, where the shading devices actually expand and contract, letting in the lighting that way. And the one on the right is actually a type of shading that falls under. So there are different types of smart facades, but really they can be broken down into two types. Macro smart facades, which have an involvement of moving parts in the device. So it's usually in addition to the building facade. And then micro smart facades, which are usually coating works like smart glazing or phase change materials. And that's where this research really goes. The general definition for a smart facade is a facade that adapts to the environmental conditions and transforms itself simultaneously. My research goes into smart glazing. So instead of adding an additional layer to the building, the research concept was, what can we do with the glazing that's already on all of these buildings, and how can we optimize it? So smart windows are a glass or glazing that respond to an external stimulus. They work much like your sunglasses, where they respond to different inputs, heat, light, etc. Brings us to a breakdown of different types of smart windows. So smart windows generally can be broken down into active and passive types, where active windows are windows that respond manually to an external stimulus, and passive, as the name suggests, respond passively without human input. So active coatings can then be broken down into electrochromic and gasochromic, which are just switched on by electricity or gas, and passive windows are then split into photochromic, which responds to incident photons, or thermochromic, which responds to incident heat. And that's really where this research focused, the thermochromic types to have that passive element controlling the heat entering and exiting the building. So thermochromic coatings are defined as variable heat mirrors whose infrared optical properties change in response to external temperature. So on the screen, you can see on the left-hand side, the schematic shows a cold day where the solar heat is allowed to enter the space. And then on the contrary, on the right-hand side, on a warm day, the infrared optical properties of the film change so that the room doesn't experience solar radiation warm-up and a comfortable interior temperature is maintained. Now, there are different types of thermochromic windows, but the literature had shown that nanoparticle thermochromic glazing technologies have the best performance potential, and that's due to their large surface area to volume ratio. Not getting too technical, that's where we delved in, and we had some research questions pop up, such as how can these nanoparticle thermochromic windows enhance performance compared to what's available on the market today? Can you incorporate this technology into a facade designed to reduce energy consumption, improve thermal loads, etc.? And finally, what were the visual effects of these coatings? How do they change how a building looks and how people feel when they're inside that building? So that brings us swiftly to material development. To do any research, we needed thermochromic windows, which were harder than we thought to get our hands on, so we went to the lab. I'll really briefly delve into some metrics because they're important for the remainder of the slides. Generally, when you talk about windows, you talk about U value, which is a measure of the heat that's transferred through the window, and solar heat gain coefficient, which is a measure of how much radiation passes through the window. But when you're looking at smart windows, you're also looking at three more metrics: luminance transmittance, which is a measure of the visible light that passes through a smart window; solar modulation, which is the capability of a smart window to regulate depending on the incoming radiation; and transition temperature, which is the temperatures at which these occur when you're talking about thermochromics. That's pretty much all the technical. Now, here's the fun. You can see the development process in the lab, where the main take home is that we use nano-sized vanadium dioxide particles to create films with variable film thicknesses. And that thickness then controls the luminance transmittance, which we got to vary from 30 to 75%, and the infrared modulating capability, which we got to vary from 2 to 6%. You can see me having fun in the lab there on the end. A little more technical, that's the development process outlined. it looks like it was all ready to go from the get-go. This was a lot of trial and error until we got what we needed from the coatings. But in short, we used HCl and ethanol, combined VO2 nanorods into the mixture at different ratios until we got what we needed, spin coated them, and dried them up so that you're left with a glass substrate and a coating with it for really simple application. And here you can see what the coatings look like. So you have the different thickness coatings, got a glass slide, and then it layered up with the different thermochromics. You can see they get darker. And for a comparison of scale, a sheet of paper is about 100,000 nanometers thick. So these coatings are anywhere from 100 to 1,000 times thinner than that. Very, very specific devices used to always get the coatings out there. Then we manufactured an in-house heating device so that the coatings could be heated and cooled so that we could take the optical readings that we needed to input the data into a building simulation. So this is, there's a lot of information that's packed into this slide, but really it's just two images overlaid on top of one another. So you're looking at the back at the solar power that reaches the Earth's surface, and that varies from 250 to 2,500 nanometers. And it's broken down into the UV, the visible, and the IR. And you can see from there that about 50% of that energy is in the visible and the other 50 is in the IR, because it drops off. And then overlaid onto the front of it are the different coatings that we developed. So a solid line is the coatings when they're off, a dashed line is when they're on. So you can see what happens is you've got a glass slide in black, and then you've got it with the different thermochromic coatings layered on, and you have more of that modulating capability as the coating gets thicker. And what's important to note here is that we tried to target the modulation to be in the IR band so that the coatings could control the amount of heat that enters and exits the building without affecting how the coating looks, so that they're not switching visibly, they're just doing their job in terms of regulating the heat entering. And that brings us to probably most of the expertise in the room now, which is you've got these coatings and they do operate. They took a long time to get operating. That might have looked like numbers on or lines on a graph, but that was 2 years of research in the making to get that Eureka, they switch moment so that we could input the data into a model to see what benefits they could provide to the architectural community. So we developed a model based off of an office building model in Design Builder, which uses the Energy Plus simulation engine. And we modeled it after a Department of Energy medium-sized office building to see the results. You can see there, the middle office was used, and it was the equator facing office that's in this diagram, but we actually oriented the building in multiple directions to see the results. So we chose to do different test locations. So for the buildings, we chose climates based off of the Köppen climate classification system that divides temperatures based off of their seasonal precipitation and temperature patterns. So you can see that we've chosen a hot desert climate in Cairo, a Mediterranean climate in Barcelona, temperate oceanic in London, and a subarctic climate for Kiruna, so that you can really extrapolate the results beyond just what happens when these coatings are in one climate to what happens when they're in different environments. The bar graphs correspond to site direct solar radiation, and the line graphs correspond to mean outdoor air temperature. So you just see a variety. And now the fun part, which is really where we wanted to see what happens to the energy usage in a building when you have these smart thermochromic windows. So the results are broken down so that you can see energy consumption on the y-axis for the different climates in Sweden, London, Barcelona, and Cairo. And they're split up so that you have a double glazed comparison and the different thickness codes, breaking that down into lighting, heating, and cooling. So you can see that the lighting load remains relatively low in all of the climates, but it's really the heating and in particular the cooling that varies most significantly. So if we take just two climates so that we can delve into them, if you look at Cairo, you can see that for a double glazed coating, you've got an energy consumption sitting at around the 60 kilowatt per meter squared mark. And then all the way down to an 800 nanometer coating, you can pretty much, not quite half, but almost half that for the thicker coatings. That isn't the case in a climate like Sweden, where even though you've got the cooling energy in the blue reducing, you've actually got heating load increasing. So it's that trade-off between what you need for that particular climate. And another way to look at that is looking at energy usage in particular compared to a double glazed window for each of those coating thicknesses. So you can see that the results show, like we were seeing earlier, that the thicker films show the highest energy saving over double glazing in all of the climates. And that's due to a combination of both visible and IR effects. But that's most prominent for the thicker coatings in Cairo versus, again, Karuna, where you see less of that benefit. And where it got really interesting is where we then went, hang on, these coatings that are getting thicker are also getting darker. What happens if you compare their benefit not against a double glazed window, but against a tinted window equivalent, where you actually hold the visible component steady, so that you're really comparing against what would happen with the thermochromic window versus the tint alone. And this was interesting because you could see that you still get more energy saving for the thicker coatings in the warmer climates, but in the cooler climates, that's not the case, where you actually have for a thinner coating, for thicker coating, less energy saving relative to a tinted window, which just translates to mean for those climates, you're probably better off from a cost perspective and other perspectives just using a tinted window. So it's really seeing where the benefit is the most to see how dark you want to go with the coating, how much nanoparticle thermochromism you want in that coating. So there's a lot of control that we should be able to have as designers, where hopefully the market will catch up. Another interesting one was peak loads. So in addition to the energy savings, we looked at peak loads in the different climates, and you can see that for Cairo, Barcelona, and London, you've got savings also in peak loads, which is important because that maximum determines the size of energy generators, transmission lines, transformers, etc. A little bit more of an investigation. And that segued into, now that we've looked at energy, naturally, what about daylighting? So you've got these coatings on these buildings, and they will have an effect on the visual comfort or discomfort of occupants. So the way we chose to look at this was to use a metric called useful daylight luminance, where we categorize the fraction of time that indoor light on a horizontal surface on the height of a working desk is given in different ranges. So if it was below 500 lux, it was deemed insufficient to be the sole source of illumination. 5 to 2000 was deemed desirable, and greater than 2000 was providing discomfort. These numbers actually represent a worst case scenario where you can have lower levels of daylighting, occupants still be comfortable. So you can see the different spread of the percentage hours in that comfortable band, where the majority of the thermochromic windows could provide improved daylighting in comparison to the double glazing and the black line there. But it's interesting that that thicker thermochromic coating in the dark blue has its most desirable range closer to the window. So you've got there, you've got the different distances from the window with the window placed on the left-hand side, and that corresponds exactly to the graph there. So depending on which coating you use, you might want to put a desk right up against the window or a desk closer to the middle of the space. So it's also about the use of the rooms being taken into consideration. And that's the same data as a daylight map, where you've got the window on the left-hand side and the different distances away on the x-axis, where you can see again the lighter area in the lighter coating means there's more of that UDI in the desirable range. I've got a question here saying, what software did you use for the energy simulations? It was Design Builder, which does run Energy Plus, which we can chat about more in the. That leads us to the final part of the research, which is we've looked at these coatings, we've developed them, and we know how they work in a building model, but what do people think of them? And I quite like this quote, which is, why would you design something if it didn't improve the human condition? Because ultimately, isn't that the whole point? So this is where the real fun stuff happens. We devised an experimental setup where we actually got different mimickings of the thermochromic coatings by controlling the CCT in the space. And we got participants to come into the space and answer a group of questions so that we could get their perception and performance in the different spaces, just to gauge an initial understanding of how people feel in the different spaces. So we asked them questions like, how does the lighting feel in the room? How do the colors look? Is the brightness sufficient? And things like that. And then we also got the performance by doing a flanker task, which was arrows that point, and you might have done this kind of for fun. There are arrows that pop up on the screen facing left, facing right, or facing neutral. And you have to immediately press on the keyboard which way they're facing so that you get people's reaction time and accuracy to see how they perform in different spaces. In addition to that, we combined the data with something called EEG data, which is used to measure an occupant's visual perception in a different space by tracking electrical signals and patterns as a result of brain activity in the different spaces. That was then compared against how they assessed themselves in the bottom right there. So you could see the different data. You could really gather a holistic picture of how people felt in the space. Without getting too technical into the results, I just showed some of the interesting ones. So on the left, you can see answers to the question, in terms of color temperature, how did you feel as a participant in the room, ranked from cool to warm? And what's interesting is that the participants correctly categorized the film that they were in the space. So they'd walk into the space, they'd have a window film, I'd take a baseline reading, and then take their reading, walk them out of the space, and change the film. And they never knew what film was being put up as part of that control. But almost all of the participants correctly identified the type of film from the feel in the space. But then on the right-hand side, you see the question, how do you feel in terms of the lighting? Is it too dim or too bright? This was, for lack of a better word, a trick question, because the illuminance was kept identical under all of the scenarios as a control variable. Yet with that said, participants subjectively noted that they thought the brightness to be higher under the higher CCT compared to the lower, which translates to thin window coatings and thicker window coatings. So it's just interesting to see people's perception. And then the results aren't on the screen, but in terms of task performance that we got them to conduct, they displayed no statistically significant difference in their reaction speed of the tasks under the different conditions or their accuracy, which suggests that, in short, even though people noticed that they were in different spaces, they performed equally, which might show more usability of these technologies if people are performing the same in the different spaces. So I guess that takes us to where to next. We've run through material development to show a simple process to get a smart window tested and up and running for practical smart window application. We've run through an exploration of building simulation insights into how these coatings would act in different climates. And I've ended with visual perception, which hopefully opens the door to architects and architectural scientists alike, considering what buildings would be like with these smart windows implemented in terms of human response to the coatings. But zooming back out, the general idea is really, the thermochromic research was for this specific PhD topic, but the idea is to be able to gather scientific knowledge to improve the human environment, because that's the space and the realm that we're all working in. So you can guess that I was very excited when I saw that right before COVID hit, this project began looking at scalable smart solutions for energy saving in building facades, where the Switch to Save project is going ahead to look into the affordability and availability of thermochromic and electrochromic coatings, assessing performance, heating and cooling energy requirements, lighting comfort in 2 real buildings in Greece and Sweden. So I'm very excited to see what the results of that show, to see if it correlates with the data that we got when these facades are actually blown up to be large-scale building windows. And from there, where's the future of smart facades? I wouldn't be able to tell you. I can only tell you some facts, that the Empire State Building was actually fitted with electrochromic smart glass as part of a major refurbishment, and it saved them $2.4 million in energy bills in just 1 year. So it got benefits there. And you're looking at so many different materials that have come up. You've got ETFE, who my colleague actually, Yen, investigated for his PhD research, and the energy saving capability of that cushion, kind of inflates and deflates. You've got self-cleaning windows coming in with titanium thin films. You've got thermometals, which use 2 different metals laminated together so that the movement of the structure can dynamically respond to the environment. And then probably my favorite, most interesting one, the micro algae cultivated in a glass facade that generates heat for the building operation, but also biomass for the food and pharmaceutical industries. So who knows where we're going from there? And I'll open it up. I'll say thank you for having me, and I'll open it to questions and hopefully a discussion between all of us.
Beautiful presentation. Thank you, Marina. I have so many questions, but I normally hog the floor. So let's see if anyone else has questions that we can start with. In terms of the technology or the materiality that goes into the particular glass you're looking at, it sounds a bit like there's potential here for the Prius effect, you know, when something is so complicated, even though the outcome is environmentally friendly. Is it something that you looked at as well, or you can comment on?
So that was one of the initial questions when we were looking at how do we develop these coatings so that we can test their simulating and architectural capabilities. So this was actually, believe it or not, one of the simpler ways to develop the coatings. They can be developed in different kinds of ways, and I think the biggest limitation, when we initially did the research, we went to different labs and said, hey, can we develop these on a large scale in your lab? And they went, actually, you're going to contaminate our equipment. So no, you cannot. So for the research, we did a small scale facade, but when actually incorporated into manufacturing lines, what I was hoping from the research is that it becomes simpler because it becomes part of a chain where you're not manufacturing just one set of these coatings, but they become manufactured on a larger scale so that you have all the technology and equipment and they become simpler to manufacture and put out there. Hopefully that answers that.
Absolutely, thanks. And we've got, let's start with the question in the chat. Thanks for the presentation. One question: in commercial building spaces, as you showed earlier, is visual comfort different between users? So if one user is sitting closer to the window, they might have a different experience in terms of glare or UV. Can we personalize that? Is there any decentralized mechanism or control that?
I love this question. I really do, because earlier in the research, I was debating, actually, research can branch in different directions. We were debating looking at electrochromic versus thermochromic. So I chose thermochromic as a passive technology that just changes in relation to heat. But there is research going around saying that it's really interesting. Occupants like to have control over their environment. So I remember reading a study where there were different people in office spaces and temperatures were set at, you know, their ideal that they had set. And they still wanted the ability to go up and press the air conditioning button up and down, just so that they had control over that environment. So I think that question relates back to that one of the, that even though the space might really be ideal for what they need to operate and perform a task or to be in that space, you might have research, and I'm sure there is, this is all a year old, and the research world develops quickly. So there's probably coatings that are looking at a combination of electrochromic and thermochromic, where you have that passive idea, but then the electrochromic aspect comes in where electricity is actually fed in so that you can switch them off or switch them on to have that controlling factor. What that does in terms of cost, etc., would be a whole other thing to figure out. But in terms of that question, yeah, I think that to have those mechanisms to control that switching might make people maybe feel more comfortable if the budget's there.
Maybe to take off from that one, can you talk about any costs that you've either experienced through research or maybe from the was the building in New York you mentioned, so the $2.4 million savings? Maybe do you know of what their cost implications were of the actual application of the coatings in the process or widely within the process of applying to a building?
It's a good question. I don't know their exact budget cost implications, but I do know the glass that they used, so I can reverse engineer the rough ballpark of where that would have sat. So I used to get asked this a lot at the end of talks, so I've just got some numbers so you can hear out the different glazings where their costs generally tend to be in the US. They've got single layered glass starts at $40 per meter squared. You've got that going up to $220 per meter squared for low E. Double glazing comes in at $300, $430 for thermochromics, and about $650 for electrochromics. So the general idea, I feel, is that it goes back to that earlier slides where all of these buildings are just clad with glass, where you can actually have different orientations that benefit the most from having that coating clad in a particular type of smart glazing. if you integrate it so that it looks like the other coating. So I think there's room for that. And maybe, I'm not sure, lack of awareness in the architectural community about how much these coatings can do, so that when you're doing a cost benefit analysis, you weigh up, hey, this is the cost of it, but this is the savings that I'm going to get in that regard.
Maybe it's in that sort of same sense too, that like if you're pulling out a whole window to then install double glazing or applying your whole panel to it, then your actual installation costs may be lower too, just to apply the film of this thermochromic coating as well too. So maybe that's the balance that where it becomes
Can you retrofit it?
So the way I did it wouldn't be retrofittable, because we actually spin coated it as a solution-based coating onto the glass. But there are films that I've seen actually pop up in the last couple of months, where you can kind of drag a thermochromic thin film like you would with any other window film and kind of stick it on. So the technology is getting there.
Yeah. Now we do have a question in the chat about how can we incorporate smart facades in interior spaces, and would there be benefits in doing that? So I guess controlling the environment internally as well. So not just the facade and how you react to external stimulus, but internally as well. You can start to create spaces, different fields of space.
Good one.
Yeah.
I think it probably depends on the type of smart facade. So when we say smart facades, like the one that I spoke about, thermochromics, because it reacts to the amount of heat that's falling in, you probably want it on an external face so that you can maximize their benefit. But some of the other ones I was talking about, like the electrochromic or even the gasochromic or photochromic, I can't see why not, because then you'd kind of get like a smart screen system as well, where you control visibility or tintability of spaces. So it doesn't just have to be heat based. Of course, if you have different elements, you can probably control the interior spaces. I'm not sure I've seen many electrochromics used in interior spaces. That picture that I had up at the start with the switching little GIF, it would probably be a lot like that.
Yeah, it'd be just like the. Now we do have a question from.
Sorry, Yaara, am I allowed to comment on that?
Sure.
Absolutely, yeah, Veronica, we would appreciate it.
Oh, I just want to say that theoretically or technically, yes, you can do anything if you want, putting thermochromic or electrochromic inside. But my question is, why? Why do you need to do that when there are probably other cheaper technologies or design solutions if you want to manipulate the feeling in the space or lighting in the space? I think there's other possibilities, because it is, as Marina already pointed out, in terms of the cost, it is still pretty expensive. It makes sense to use it because of the long-term benefit. And as she showed, in terms of long-term energy consumption, and if you convert that into cost, obviously that becomes cost benefits. But if there is very little benefit that can justify the use of thermochromic or electrochromic glass inside, I would ask, do you really need it? So theoretically, of course, you can.
I'm glad
it really makes sense.
Yeah, thanks, Veronica. I'm glad you went down that philosophical path of why, because Ken has a philosophical question as well. Ken, do you want to unmute yourself and ask your question?
Yeah, thank you very much. I just had a quick question from Marina's and anyone else's point of view around, if perhaps we actually have facades that are able to adjust themselves, and especially, I know with the glass, thermochromic glass, it actually reduces a lot of moving parts. So you also mentioned some active facades that can actually move and stuff like that, which is super cool, but can have maintenance problems. But if all of a sudden glass can do all these fantastic things, and they can be thermally broken, sometimes you start that comes part of like the rationale, right? It's like, do we need all this shading outside? Do we need to orient the right way? Do we need to include different passive design elements? So I just kind of wondered, and that kind of takes away from like regional, like architectural aesthetics and identity. So I was wondering if I could just throw that one up there, because I can kind of see kind of like both ways where if perhaps you're trying to make a very modern building, that can be an option, or if you're doing like a cultural uh, heritage kind of adaptive reuse, you don't really want to do too much in terms of like changing the character. So you can just put up like a glass wall. But I was just wondering what people thought around like an all glass solution versus good passive design as well. And is there a good happy medium?
I can start this answer, but then I'll definitely throw it to Veronica and anyone else who wants to answer from this. I think it's the whole, why not both? That you have these smart glazing technologies and smart facades, but it won't replace the need for ventilation in a space or other aspects that passive design really focuses in on. That's not my area, so I definitely would throw that to someone else in the chat. But the one that you touched on there was, for example, would you consider a tinted facade as not usable in a regional building, or would that be fine? And is it just a technology that's still a little bit sci-fi, that we have these smart facades that people aren't comfortable yet using? So yeah, food for thought, and I'll leave that with Veronica and anyone else.
I mean, the main reason why I bring that up, right? Because like, especially if you're thinking about cost, and I think you hinted at this, is that if you can actually reduce the cost of, you know, some other elements and potential maintenance, then that also kind of becomes part of the rationale of going down this realm of investing a little bit more into how does that glass perform. And, you know, once again, we've talked about this in other kind of like sustainability sessions around thermal bridging and things of that nature. So if you can actually include all of that in terms of a facade element, then you kind of have like a win-all situation. And then from there, you're like, well, are we doubling up on these other kind of passive elements? So I think I totally agree that it's really good to have like a hybrid kind of thing, but then it could easily become part of a trajectory of, oh, if we just make sure the glass and the facade is all good, we don't have to really think of these other bits. But yeah, in terms of like our own professional practice, we need to really see what is those kind of balance points are.
Yeah, I guess that brings us neatly back to Veronica's point of why. Why would you do that?
I think my view, Ken, if I may, again, it depends. If I were to design a residential building or 2-story, even 4-story, I would say, do we really need to use this? Because there are other ways of doing it, perhaps also more aesthetically. People are more engaged to be involved, let's say opening the windows or putting shades down and so on, and it's more a livable place. But when you start talking about 20, 30-story buildings, I think the example that Marina showed in the beginning is clearly showing that in a particularly public building or a commercial building where not everybody would like to be engaged with the building facade because it's harder, it's outside, you know, you don't expect people to go out and then pull down the shade because they might fall out from the building, or it becomes too expensive to do this sort of external shading and so on, which is more applicable for small scale buildings. Then I think smart facade like this or smart glazing becomes more reasonable to use. So again, I guess it depends on the context where it is. And there are other ways, obviously, to design the building. But when it comes to, and then you already touched also a bit, maintenance. I think the benefit of this compared to, let's say, the smart facade with the movable shading, even though architecturally it probably looks more appealing and looking smarter and more sort of inspired by the local architecture and tradition, because that's how the Alba Tower, I think it uses the local pattern of the rug or something like that. It's something to do with the traditional craft. But I can imagine it is pretty expensive to control it. And I also think for that building particularly, even though I think it is using sensor, but what happened if the sensor broke and then it didn't work and then it just doesn't want to open or close the shading? Whereas the smart glazing, the thermochromic at least, it doesn't rely on that further or electronic system. And that's why I think the beauty of thermochromic is that. But once again, I would not put that in 1-story building or 2-story building because it's not necessary. That's my view.
Thank you, Veronica. And we've got time for 2 more quick questions. One is from Renee. So Renee, if you want to jump in.
Yeah, so my question was how resistant is it, the coating in terms of mechanical impact, but I would assume if it's double glazing, that's probably on the inside. It's not really under the influence of any external impacts, isn't it?
That's exactly it. When we did the modeling, we did it on the different layers, but ultimately what you find is for that exact reason you want it on the inner surfaces. So we had it on the inner face of the outer surface of the double glazed unit so that it resisted mechanical impact.
All right, thanks.
Thanks for that. And we've got a question from Dean. I think it's the last question we've got time for. So Dean, if you want to mute yourself, or would you rather we read out your question?
Hi, everyone. I guess, well, I had a few questions there, but I guess the one I'm most interested in is if I wanted to use this type of glass, like who are the suppliers or manufacturers in Australia to talk to? Like, who would you recommend?
That's a really, really good question. So when I was doing the research, there were several scattered manufacturers. You could Google, thermochromic glazing in Australia, and they would pop up. But what you really want is something certified. So I know that Window does a certification of, legitimate thermochromic coating companies. I could probably dig them up if you're interested specifically in thermochromics. But it would be a search to make sure that they've got all of their data available online, that they're not just advertising a smart window, but they've actually given you the data so that just like I did, you could input it into your own building models and have the real aspects of the glazing come up. So that would probably be the stamp of legitimacy, that they give you all of their switching data so that you can model it.
Okay, great, awesome.
So
we've got plenty more questions for you, Marina, but we might take them offline and do this another time. And I'm sure everyone else would like to thank you as well. We've got a few thank yous coming in the chat. And
similarly, like with our other events and for this one too, keep in tune with our social media pages, LinkedIn, Facebook, Instagram, and for all our upcoming events and past items as well too. And
tell all your friends about us as well.
Absolutely, that's how you expand the network. So.
Yeah. Very good. Excellent. Thanks, everyone.
Much appreciated, guys. Have a good day. Thank you.
Thank you.
Bye.